All right. Thank you.
Make it out of cutting block?
It's just a piece of wood. It looks like a cutting board, though, doesn't it? Nice finish on it, huh?
Kind of looks like the pictures thing, like used to paint stuff.
It is. Maybe that means I should get into painting. What is that called? Yeah, I know what you're talking about. Where they put all the paint all over it. Okay. All right. All right, everyone. I have a couple of things for you. I have your not quizzes, bonus questions from last time. Those have been graded. Now, I would like to just ask you if you have a preference on, do you want me to call names or can I just pass these around? I mean, some people are like, I don't want people to see my grade, and that's okay. But, for me, it's better if I just pass them around because it's faster for me. Is that okay with everyone? Any objections? It's good? Okay, here it comes. Just take yours. Yeah, these are all bonus. There may be more than one bonus in there, so go through the whole stack. The next handout I'm going to give you at the end of class. Do not let me forget to give this to you at the end of class. We have our mini exam number 1, which is due on Wednesday, right? So I sent out an email about it a couple of days ago, trying to get you to get going on it. Hopefully, I talked to a few students, and it looks like I'm getting the sense that a lot of you have worked it out, at least tried. What we covered today, 10.5, should cover the whole thing. So you'll come in on Wednesday, you'll hand it in, and I will trade you. I will hand you your next one. So that's pretty much the way it's going to work all semester. You hand one in, I hand you the next one. And we keep rolling like that until the midterm. All right? All right, let's see how my technology holds up here today. I do them all out of 100. It is great, but then, we'll take the number of bonuses we have at the end, and I told you the most you can get is 10 points added onto your final grade, right? Yes. No, midterm and final will be a little different. They'll be a little bit more like the book problems, and it's all about time, because some of those problems on the mini exam may have taken you a while to figure, to get through. But if you can do all the problems from the mini exams, my opinion is that the other stuff is pretty trivial then, once you get to the midterm. Okay? Try not to be in your way here. I am somewhat portable here. Okay? All right, here we go. Equations of lines and planes. I think this is probably the most important section of the chapter, right here. So chapter 10, this is the big one. So we're going to start off with, everyone has the notes from last time I handed out? Anyone need 10.5? Open that filing cabinet. On the top left, I believe there's a stack of things, and I think 10.5 is in there somewhere. Anyone else need 10.5? I've got several copies, so do you see it? 10.5? I think it looks like that's okay. Just you. And after class, there's like 10.6, 10.7, 10.8 in there. You can take what you need out of there. Okay, so the preliminary concept here, given two vectors, okay, given two vectors, we'll call that R0 and R1. If we compute the difference between the two vectors, the resultant vector is equal to a vector from the tip of R0 to the tip of R1. All right, so what we're saying, I'm going to practice my drawing here, see if this works, okay? Yeah. If we have R0, and we're going to have pictures on the next page, but I'm just like playing with my marker right now. R1, R0, then if you do R1 minus R0, you get this vector, the one that connects the tip of R0 to the tip of R1. That would be R1 minus R0. Do you agree with that? Well, let me go through the next page and hopefully it'll be illustrated, all right? So let's look at this. Hold on. Let's say we're trying to define a line. How do we define a line in college algebra, in pre-algebra? What do you need to define a line? 2 points, right? 2 points. That's it. Give me 2 points in two-dimensional space or three-dimensional space. There is a unique line through 2 points. Agreed? Okay, in Calculus 3, it's kind of the same thing, but now we're going to talk about a different type of equation for a line. Our standard equations for lines, the things that we've used our whole lives, what was always our standard equation for lines? What did they look like? Like y equals mx plus b. Okay, this is called a linear equation. Linear equation. We are going to be talking about vector equations for lines today. Totally different thing. All right, totally different. It involves vectors. So taking a look at this blue line here, we want to notice that at every blue point on this line, there is a vector that goes from the origin to that point, right? And as we add more and more vectors, we can see, every one of those points lives on that line, right? So there are infinitely many vectors that create that line. Do you agree? Every single one of those vectors lives on that line, or the tip of it does. All right, next. The vector equation of a line is an equation which will generate all the vectors that go from the origin to every one of those points. So our equation has to be able to generate all those dots, all those vectors I just drew. That's what our equation has to do. So here's how we're going to get it. It's going to take a little bit of work, but we'll be able to get it, all right? The first thing we're going to do is we're going to say we have a point on the line. I didn't label it on your notes. You'll probably want to label it x0, y0. That is a point, right? Not a vector, a point. We start out with any point on the line. And then imagine the vector that goes from the origin to that point. So if the origin is 0, 0, then what is the vector R naught here? The vector. It's x0, y0, isn't it? All we're doing there is we're subtracting the coordinates, right? We're taking the x0 subtracting 0. We're taking the y0 subtracting 0. And then we get that vector. Okay? Everyone clear, okay with that? R0, okay, this vector here, is created by taking the point x0, y0 and the point 0, 0 and finding the vector that goes from 0, 0 to that point. So you subtract coordinates.
That doesn't matter which way you go?
It does matter, absolutely. If you go from, here's the computation. That's the computation going from 0, 0 to x0, y0. If you went the other way around, it would be 0 minus x0, 0 minus y0, so they'd be negative instead. All right, so that's where we're starting, right? Next thing we're going to do is we're going to pick a second point. All right, we're going to pick a second point. Got to clear all this junk off my screen here. We're going to pick a second point, which is x1, y1, and create the vector that goes from the origin to that point, which would be R1. So same exact concept. So 2 points make up a line. We've picked 2 points. We've created 2 vectors from those points. With me? Now let's look at the computation of R1 minus R0. This is what I was asking you to look at just a second ago. What is R1 minus R0? I tried to do this as best I could with my drawing up here. I'm going to do it a little different right now. I'm going to highlight for you. R1 goes here to here, right? That's R1. So that's R1. Now, if I add R0, I would go tip to tail, right? So I would add R0. Wouldn't that put me up here somewhere? That's if I added R0, because R0 is this guy right here. If I add it, I'd be up there. But I want to subtract it. So instead of having that yellow pointing up like that, it's going to point down. I have it labeled right there. The resultant vector is V, which is the red one. Go with that? You'll see the picture? So that red one, V, is R1 minus R0. Now we're going to need that. Get all this out of here. Because I think in the next step, I'm going to translate this V. I'm going to take that V that was down there. Remember, vectors can move around, right? So I took that vector that was down on the bottom here, and I moved him up. Whoa. So V was down here, right? I just moved that sucker up like that. Y'all see it? So V, interestingly enough, lives on the line that we're talking about, doesn't it? The blue line that we wanted, that vector V runs parallel to it. In fact, hopefully you can see this now, that R1 is now the R0 plus the V. Y'all see that? All right, we're getting somewhere here. Do I have any questions, though? Now, I want you to notice that if I take the R0 again, right? This was R0 plus V. What would R0 plus 2V be? Well, it would get you to that point, right? Which, again, lives on that line, doesn't it? What if I did R0 plus negative V? Where would I be? So now I go R0. Here's V, right? Negative V is pointing the opposite direction, but where does that take you? To another point on that line, right? So what I'm trying to get you to see is that R0 lives on the line, right? R0 plus V lived on the line. R0 plus 2V lived on the line. R0 plus negative V lives on the line. So what do you think would create the line then? R0 plus TV, where T is a number, a scalar. Isn't this R0, that initial vector, getting you up to the line, and then isn't T times V all the scalar multiples of V, which takes you out in one direction forever, in the other direction forever? The next illustration will show that. Let me get you to the, where's my picture? I think it went too far. There it is. Okay, so there's R0 plus 1V. Now you can take this little dragger here, slider. You can see that any multiple of V takes me up one direction and then opposite direction. That will create all the points on that line. So I'm just changing T right now in the formula. Y'all see that or not? Y'all are so quiet. I can never tell by looking at you. So T is like a time. You could look at it as time. A lot of times we will, but it's just a general scalar for us right now. All right. So I want to draw something here for us. Actually, I want to highlight something for us. This right here is our big equation from so far. All right. This is the general form of a vector on this line will be this. So that's our vector equation for a line. It is R of t equals R0 plus TV. And this is like a function, okay? It is, right? It takes on a value t. Once you plug in a t, it spits out a what? What does it spit out over here? Like if I plug in 0 for t, what comes out? R0. R0 is a what? It's a vector, right? And that vector lives on that line, right? Okay. If I plug in 1 for t, then I get R0 plus some scalar multiple, so plus V. That will live on the line. So we have now, instead of that linear equation that we had, y equals mx plus b, we now have what we call the vector equation or vector function of a line. Now the v in the problem, the v has a very important name. It is called the direction vector or the direction of the line. That v determines everything about the line, right? Once you have v, you've got which way it points. The R0, that vector, basically is a point, gets you to a point on the line, and then the V takes over and points you in the right direction. So if you look at it like this, if somebody gives me a point, boom, there's automatically some vector going to it, that's R0. Does that point define a line? No. All I need now is for someone to give me what? A direction. As soon as you give me a direction, I'll just pick direction. Let's point it this way. Once I have a direction, I'll call that V, then everything that lives in the direction of that vector through that point creates my line. So this is our line right here, through here. So in college algebra, what did you need to define a line? A point and a slope or 2 points, right? In Calculus 3, what do we need to define a line, the vector equation of a line? A point and a direction, which is kind of like point slope, but it extends into 3 dimensions now. So we can start with any point and a direction vector, and there's a unique line through that point with that direction. The magnitude of V? Yeah, it just gets us, it gives us a starting, like, because if I just say point in a direction from the origin, then all you have are all the lines through the origin. What we need is, sometimes our lines don't go through the origin, so we need to get off the origin, so R0 takes us out to a point. Good question. All right, let's get out of this. So this is kind of summarizing what I just said. It's the direction. R0 equals that x0, y0. V, we like to label it, since it's a vector in 2-dimensional space, at least what I've been showing you, we like to label V as the vector AB, so it has the components AB. If I take my R0 and I plug in R0 right here, if R0 is the vector x0, y0, and V is the direction vector AB, then if I put those together in that formula, isn't this R of t equals R0 plus TV? Isn't that R0 plus TV? And if we distribute our t through the second vector, we get what? AT, BT? And then add the 2 vectors together with vector addition, and you get this. Right? It's the x plus the AT, and then the y component is y0 plus the TB, or BT. So that's another way of writing the vector equation of a line. All right. If we do that, the x component is that x0 AT, x0 plus AT, and the y component is y0 plus BT. In other words, if we have the vector equation of a line, if you take the x and y components, the x component is x, the y component is y. These are called parametric equations. So in order to know what your x is, you need to know x0 and AT. And then to know what y is, you need to know y0 and BT. This is for 2. The next note takes us into 3, I believe. We'll get to an example also. No, this is the vector equation up here. That's the vector equation. If you take just the x component right here, that's x, right? X naught plus AT is x. Y naught plus BT is y. So that's what this says. X is x naught plus AT, y is y naught plus BT. Those are called parametric equations. And yeah, R of T is your vector equation. Uh-huh. Yes, you should be able to do that. And there's another one coming too. There's called the symmetric equations. So any of these three are fair game. Now let me explain what a symmetric equation is. Since this first equation here has t in it, right? This parametric equation has t in it, and this parametric equation has t in it, we can solve them both for t, couldn't we? And if we can solve them both for t, then we can set them equal to each other. So how would you get t by itself in this first equation up here? Move x0 over, right? So subtract x0, divide by a. Isn't that this right here? How would you solve for t on the second one? Move y0 over, divide by b. That would be equal to t, so you set them equal to each other, and that's what we call symmetric equation. Notice that the symmetric equations don't have t in them, right? Because you've set them both to t and then set them equal to each other. Y'all follow that? All right. Now, everything we have here extends into three-dimensional space. So if we start with a vector r0 and then a direction v, we have a vector equation. So the only difference here is what? Third component, right? z0. Over here, instead of ab, we have abc. And then when you put them together, you have 1, 2, 3 parametric equations. One for x, one for y, one for z. Right? And you can solve each of these parametric equations for t, and you can set them equal to each other, which means that you should have, your symmetric equations should contain 3 equations. Also, the numbers a, b, c, they call them the direction numbers. Why do you think they call them the direction numbers? A, B, C. That's the direction vector, isn't it? So they call them the direction numbers. Damn, that, you know, for once they actually are, you know, did something that made sense. All right. Now this is a short note. It's real quick, but it's interesting. A vector equation of a line draws the whole line, doesn't it? Draws the whole thing. But sometimes you don't want the whole line. Sometimes you want a line segment that only goes from one point to another. So the way that I have this here is, let's say that we have 2 points, right? And we only want the vector equation to go from one to the other. So I'm going to call this R0 here and R1. Now, R1 and R0 are not points, okay? Keep in mind that what's actually happening here is that from the origin, we have a vector and a vector like that, right? That's what's really happening. But if I want just that segment, I don't want to extend this line out forever in each direction, then all I have to do is restrict the domain of my vector function. Remember, t could be any number that would scale that v. All I need to do is make sure that I restrict that t so that I don't go out forever in both directions. And the natural choice is to go and restrict your t from 0 to 1. And this is the one I think that makes hopefully the most sense. Look at this right here. This is really TV right there. Okay, that's really TV. Remember, V was the direction vector? So what this says is that if I let t be 0, where will I be? If t is 0, where am I? R0, right? If t is 1, what do we get? You get R0 plus R1 minus R0. Well, what's R0 minus R0? Gone, right? So all that's left here is what? R1, which means you're at R1. And then if you were to plug anything in between 0 and 1 in, you'd be getting multiples, right? This blue one right here, that's 1 times V, isn't it? What's half of V? This one, right? What's a quarter of V? That one, right? I could do this all day. Anything between 0 and 1 will get me all of the points in that line segment. So that's what this note says. Anytime you want the vector equation of a line segment, you're going to have to restrict your domain on T. I think it's time to do some examples here. Okay, find the vector equation of this line. So what do I give you in this problem? 2 points. So what we want to do is this, and I'm not even going to plot these necessarily in the right place. I just have 2 points, don't I? I'm going to write them 3, 6, 7, 14. I want the vector equation of the line through those points. So there's some line that goes through these forever and ever in each direction. What's the vector equation? Well, what are the 2 things that we need for a line? We're going to need a point and a direction. Actually, we're going to need a point so that we can get R naught, and then we're going to need V, which is our direction. This is what we need, right? We need that. Well, what about an R naught? Can I create a vector that goes to one of those points? Okay, someone give me an R naught then. The vector 3, 6. Is that the only R naught I could have used? I could have also used 7, 14, right? Just a vector that goes from the origin to either one of those points. Okay, good. That's R naught. Do y'all need to see it visually? That is R naught. Now, we need V. V is a direction vector. Isn't the direction vector the same as the vector that goes from here to here? Sorry, I kind of overemphasized that. Isn't that V? How would you get the vector that goes from 3, 6 to 7, 14? Subtract, right? So isn't V the vector 7 minus 3, 14 minus 6? Isn't that the vector? Which is the vector 4, 8. That's supposed to be an equal sign here. And we said that's all we needed for the vector equation, isn't it? I mean, that's what we said. That's what I said. So I'll put it on the side here. I'll put it in black. R of t is equal to R naught plus TV. That's the equation everyone here needs to know. This is R of t equals for us R naught, which was 3, 6, plus any scalar multiple of V, which was 4, 8. And now let's start putting things together. R of t equals, let's see, how about, I'll try and take this a little slower. 3, 6 plus 4t, 8t. Right, just distributing the t through. And now add these together component to component. I'm going to jump over here. R of t equals what? 3 plus 4t or 4t plus 3, right? Addition does not matter. Okay, you can commute it. And then 6 plus 8t. Hey, what are the direction numbers? 4, 8, right? Okay. Just trying to get some language going here. Direction numbers here were 4, 8. Notice that 4, 8 actually appears here, 4 and 8. Aren't they the numbers in front of t? They should always be the numbers in front of t. Those are always going to be your direction numbers. Okay, so have we answered the first question? Find the vector equation of this line. There it is. That's it, right there. So we have answered the first question, and we're happy. Now, I'm going to try this. I'm going to do a quick screenshot and save that for later. Okay. Now I'm going to clear it and go to part B. So for part B would be to find another point on the line. Another point. Well, our vector equation was this, which I've already forgotten. It was 4t plus 3. I'll do it backwards now. And then 8t plus 6. All right. All right. Find another point on the line. Plug in whatever you want for t. Well, don't plug in 0, because what happens if you plug in 0? You get 3, 6. We already had that point. What happens if you plug in 1? You get the other point. So don't use 0 or 1. Use something else. How about 2? So now you can pick anything, any number you want, except 0 or 1. So R of 2 creates, see, plug into 8, 11, to what, 16, 22? 11, 22? Now that's a vector, right? It wanted a point, so technically I shouldn't answer it that way. I should turn it into an ordered pair. 11, 22 is a point on the line. Part C. Find the parametric equations of this line. Well, the parametric equations, all those are the x, right, and the y components of the vectors, right? That's all they are. So x is, what? 4t plus 3, and y is 8t plus 6. Nothing really going on there. Part D, symmetric equations. Solve each of those for t. So what? What would that first one be if we solve it for t? X minus 3 over 4. And that's equal to t, right? But what's t equal to on the other one? Y minus 6 over 8. Y minus 6 over 8. So we really don't even need that t in the middle. I was trying to show you where they came from, right? And we're done. Okay? Is that pretty straightforward? All right, good. Now all we do is we go to 3D now. Okay? Yes. Go back to what? Not easily. I have to bring up the picture and everything. What do you want? The work I did on A?
On the last part, was it the vector times t is equal to 3 plus 4t for x, and then
6 plus 8t.
Was there anything after that?
Nope. I mean, you could put, if you wanted to, and we didn't do this, you could have put in here next to it t element real numbers. In other words, that's the vector equation with t being any real number. Just to stress that it's a scalar. You don't have to. But if it's going to be a line segment, you need to restrict t. So if it's a line segment, you would need to let me know t is between 0 and 1. Like, you'd have to show that restriction. Okay. All right, let's look at this one here. The points 3, 6. Oh, wait, this is the same one. Yeah, next one. So I'll move a little quicker through this one, all right? What is it that I need? Point and direction. So part A, I need R naught. R naught, hey, let's go with 3, 6, negative 4. That's the vector R naught. How do we get V? The direction. The vector connecting the two, right? And it doesn't matter which one. You can go from one to the other or the other one. It doesn't matter. They're parallel vectors. So direction, this way or parallel pointing the opposite direction is the same thing. So I'll just go from 3, 6, -4 to the other one. So a quick little subtraction creates the vector 4, 8, what is that? -3. So my vector equation is R of t equals 3, 6, -4 plus t times this direction vector, which is the vector 3 plus 4t, 6 plus 8t, and then -4 minus 3t. Y'all agree with that? That is a plus right there. It's actually a mess. Let me try and get rid of it. There we go. What's that? Yeah, this is the vector equation, so it's going to be a vector. And then again, you could put in here, t element of the real numbers. That's our vector equation. Part B, parametric equations. What are the parametric equations here? X equals, so part B, x equals 3 plus 4t. Y is 6 plus 8t. Z is -4 minus 3t. I mean, once you get the vector equation line, part B and C aren't really even that challenging to us, right? Part B especially, all you're doing is looking, what's the x component, y component, z component. Now solve each of these for what? T, and set them equal to each other. Those are our symmetric equations, part C. X minus 3 over 4 equals the next one. Y minus 6 over 8, good. And then finally, z plus 4 over -3. The thing about the symmetric equations, check this out. The direction numbers always appear in the denominators here, right? 4, 8, -3. Wasn't that the direction vector? Okay. Now something a little more interesting. Find where this line intersects the YZ plane. So you've got a line in three-dimensional space, right? We have the vector equation of it. And I want to know where it hits the YZ plane. So going back to our drawings, here's X, here's Y, here's Z. And the YZ plane is this plane, right? The back wall, I guess you could say. This plane right here. I want to know where that line comes in and hits and punches through that plane. Where does it happen? So what is it about, if you had a line in here, I'll do it in green. Let's say we had a line that came through here and punched through that plane somewhere around right there. What could you tell me about that point? The x component is 0, or the x coordinate of that point is 0, right? So to punch through the YZ plane, x must be 0. Now that's very valuable to us because if we come back here now, sorry, I've got too many things in my head right now. We come back to this one right here. That was an equation with x in it, right? If we set x to 0 there, can't we solve for t? Once we know t, can't we go back to our vector equation and plug t in for every one of the components, and that would tell us where we are? That's what we're going to do. So right now, I'm going to say that on the YZ plane, implies that our x value must be 0, which implies that 3 plus 4t must be 0. That parametric equation for x, we're using it to get a t. So what is the solution for t there? So t must be negative 3/4. That's not the answer to the problem, right? That's just t. Copy that. Okay, I'm going to clear this. So here's where we are now. Do I want to do it that way? No. Someone give me the parametric equation for y. Y was, what was it again? 6 plus 8t. That's the y, is that right? Okay, yeah. So we already know what the x value is, don't we? We're punching through the yz plane. We know x is 0. That's what we set the x component to 0 to get t. So if y is this, and I know t must be what? Negative 3/4, so just plug it in. So what would y be? 6 minus 6. It's 0 again, right? So y is 0. Coincidentally, it just happened that way. And then what about the z? What was the parametric for z? Minus 3t. So when we plug in negative 3/4, we get negative 4 plus 9/4, which is negative 16/4 plus 9/4, which is negative 7/4. I really do have decent handwriting. It's just so hard to write on this thing. Yeah, it's still legible, right? Okay, so what is the point? Because it asks, find where the line intersects the yz plane. What is the point where it intersects? What's the x, y, and z? 0, 0, negative 7/4. That's where it hits. That's it. That's the z-axis, isn't it? It actually hits the z-axis. But it also punches through the plane yz there. All right, moving right along. Determine that these lines are skew. Skew meaning they do not intersect, they are not parallel, and they are not orthogonal. Now notice L1 and L2, I gave you vector equations for each of those. Now the equation's not there, but just imagine that it was actually, equals, let's say call this R1 of t. Don't I have a vector and then I have the x component, y component, z component? They both contain t's in them and numbers. So that looks like an R of t that we just had a minute ago. What's the difference between L1 and L2? A different variable. Now, why do you think it's important to have a different variable if I have a different line? It's to make you understand that the t is different for each of these. Okay, so like let's say they both had t in them. Then you might think that when I plug in t into both of them, like let's say I plug in 0, that they should both be at the same place or something. It's to distinguish the variables so we don't mix them up later. And we can use anything we want for that variable. We've been using t, but s is as good as t. Okay, how am I going to tell whether or not they intersect each other? Let's start with that. Set them equal to, how do you set vectors equal to each other? Yeah, do you agree that where these two lines, if they hit each other, if they do, which we're told they don't, right? But if they did hit each other, And these are three-dimensional, aren't they? They're in three space because they have three components. If they did hit each other, do you agree that at that point they would have to have the same x, the same y, the same z? Yes? That means I need the x, y, and z components to be simultaneously equal to each other. So let me see what that would require. Let's start with the x components. Could I ever make these equal each other? Well, let me see. 1 plus t, could that ever be equal to 2s? What type of equation is that? It's a linear equation with two variables, right? How many solutions are there to a linear equation with two variables? Infinite solutions, right? There's an infinite number of ways that we could get those two to match. I mean, just think about it. What about t is 1 and s is 1? Would that work? How about t is -1 and s is 0? That would work, right? And I could go all day. That's a linear equation, two variables. You can't, there's not a unique solution to that. Now, we have another condition, though. What's our next condition? We need the y components to match, don't we? At the same exact time, we need the y components to match. So let's set up that equation. -2 plus 3t equals 3 plus s. That color comes out all right. A little bit. I mean, we're not going to do partial fractions. This is really a system of equations is all it is. We have right now two equations with how many unknowns? 2. Can you solve a system of two equations with two unknowns? Yes. So let's try and solve it. How would you solve this? And this all goes to your background. You know, there's substitution, there's elimination, and there's calculator. So however you want. If you remember, like in college algebra or something, they put that in a set of braces, and then they said, here's your system of equations, solve. I'm going to do substitution. I think that's what I'll do. I'm going to take my first equation here. I'm going to solve it for t. T is equal to 2s minus 1. Do you agree? Now I'm going to take my second equation, and I'm going to plug in what I just found for t into that equation. So I have -2 plus 3 times 2s minus 1 equals 3 plus s. Did y'all see that? I replaced t in the second equation by what I just said the first equation was when I solved it for t. Now, tell me what that is. What type of equation is that? Linear equation, one variable, right? My 0310 class can solve that, I hope. Plus 6s minus 3 equals 3 plus s. Let's move things around here. 8. Is that right? 8 on the right side, 5s on the left. So s is 8/5. If s is 8/5, what's t? So go to this equation right here. The t we had here depends on s, right? So what's 2 times 8/5? 16/5. 16/5 minus 1, 11/5. Hey, it's looking like I'm finding something that's going to work here. Yeah, but we got a problem. Because we can make the first two components match right now. If I choose t to be 11/5 and s to be 8/5, the x and the y components should match. I mean, you can try it for yourself. I'm not going to do it, but take 11/5 and replace your t's in the first line, in the first two components, replace them with 11/5. Take your s's and replace your s's with 8/5, and the first two should match. But we haven't looked at the last one, have we? The z component. And what's going to happen is when we look at the z component here, we're forced to have to use this t and that s. But what happens if you plug in 11/5 to this right here? What do you get? 4 minus 11/5? Nine-fifths, right? Okay, we need the second one to match when I plug in what to it? 8/5. What's -3 plus 4 times 8/5? So that's -3 plus 32/5, right? 17/5? It's not the same. So even though I can find a t and an s that make the first two components match, I can't make the third one match. And if you found something that made the second two match, you couldn't find something that makes the first one match. So you can't get them all the same at the same time, which means they don't hit each other. So they do not intersect. So I've shown that. Now what? Questions on how to show two lines don't intersect? How do I show that they are not parallel? Yeah, but these are you would be trying to take a cross product of things with variables in them, wouldn't you? Think about two vectors. How do I show that they're not parallel? They're not scalar multiples of one another, right? They're not scalar multiples. So let's take a look at this first line here. Tell me the direction of that line. What's the v for that line? What's the direction vector of line 1? It's what? 1, 3, -1. Those numbers were being picked off the coefficients of t, right? I know that that's the direction that L1 points. Do y'all know where I got those numbers? Okay. What's the direction of the other line? Two, 1, 4. Okay. How can I tell if those are parallel or not? Are they scalar multiples? No, right? The only way that you're ever going to get this 1 to become a 2 is if you multiply it by 2, right? But then you have to be able to do the same thing for all of these, and they all have to match. So they're not scalar multiples. So the directions are not scalar multiples, which means the directions are not parallel, which means the lines are not parallel. Do y'all see that? So V1 and V2 are not parallel, since not scalar multiples. Another way of saying this, I did this in my notes whenever I was doing the homework. I said this instead. They're not parallel, okay, because there does not exist a C. There does not exist a C such that V1 equals CV2. Just some notation. V1 and V2 are not parallel because there does not exist a scalar such that they're scalar multiples. So I've got 2 of the 3 things. Last one. What's the last thing I need to show? That they're not orthogonal, right? How do you check? What's the orthogonality test? Dot product. You need the dot product to be 0 for orthogonality. Yes. Oh, but two orthogonal lines cannot intersect like this. See those? They don't hit each other, right? But they're perpendicular. Now, if I put them on top of each other, that's even better, and then it's a nice little cross. But if you can pull them out, they still aren't intersecting. So just because they don't intersect is not enough. We still need to check the directions. So we're going to do dot product on what, though? On the direction vectors again, right? So just take the direction of the line, dot them off. And you can even see it right here. I don't think we have to even do it separately. Multiply 2 plus multiply 3 plus multiply -4. Does that add up to be 0? No. Therefore, the dot product is not 0. It's not orthogonal. Lines that don't touch, don't intersect, aren't parallel, and aren't orthogonal or skew lines. Questions? I'm moving on. Planes. Finally. All right, we've seen in three-dimensional space, we've seen that in 2D or 3D, all we need to define a line was a point and a direction, right? A point to get a vector and then a direction to tell us which way to go. Now, what do you think you need in order to define a plane? And what we mean by plane is what we've talked about, flat sheet extended in every direction forever. What do we need to define a plane? 2 points enough? Not just 2, right? If I take this plane right here and I take these 2 corner points, that's not enough because every plane that rotates around that axis right there goes through those 2 points. So 2 points isn't enough. 3 points is what you need. 2 points to get a line, but you can't uniquely define a plane with just 2 points. So we're going to need 3, but it turns out we're actually going to need a little less than that, but let's just go with this. So here, I think I have this here. Here's our plane. Let's see how this works. Okay. Do y'all see my plane? There, it's flat. There's my three-dimensional plane. Got 3 points. Here's how we're going to kind of look at things. I can always create vectors going from the origin to all 3 of those points. I'm going to have to spin it. Do y'all see the 3 vectors? So every point can be looked at as a vector. Then I can create from one of the points here, in this case, the tip of the black one, from that one to the other 2 tips, I can create these red vectors. Now those vectors actually live on the plane, don't they? Like if I turn this, see the red vectors are in that plane? See it in there? Now I'm going to take those other ones out of there because they're just kind of getting in my way now. Those 2 red vectors live in my plane. What would happen if I take those 2 vectors and I cross the 2 vectors? Cross product. What happens? Cross 2 vectors, you get a 3rd vector, right? And it's perpendicular to both. So wouldn't that pop straight up out of the plane? Do y'all see it? That is called a normal vector to the plane. So every plane out there, pick any plane you want, orient it however you want, 3-dimensional space. There is always a vector that sticks straight out of it, right? There it is. Now you can slide it around, you can take it to the other side, but there is only one vector that's perpendicular to the plane. Do y'all agree with that? I think there's only, any scalar multiple of this, but there's not another one that does that, that's perpendicular to the plane. There's only one. That's a pretty big deal. So it turns out that in order to define a plane, we actually need less than you would think. All you need is a single point. That's it. 1 point on the plane and a direction vector. That's, well, I should say a normal vector to the plane. That's any vector perpendicular to the plane. So again, if I pick a point out in space, right, here it is, my hand, and I say, all right, point it there. There's the normal right there. Then the only plane that could go through that point and have that as a normal would be about this plane right here. Do y'all see it? That's the only one that could work. It seems like not enough information, right? Just a point in the direction, but that's all we need. Now we have some language here. If x0, y0, z0 is a point on the plane, and now this new notation n, the vector n, is equal to ABC is any normal vector to the plane. Normal means, in this case, perpendicular or orthogonal to the plane. Then the equation of the plane is as follows. A, in parentheses, x minus x0, plus b, y minus y0, plus c, z minus z0, equals 0. And I put here, notice this is not a vector equation for a plane. This is actually a linear equation. So if you studied planes in the past, you know it's got x, y's, and z's and equal to a number. That's pretty much what we're going to be working with here. But we can get the equation using the idea of this normal vector. So if we take this equation here and we distribute through the a, the b, the c, we get that equation here. And what we'll notice is that the ax0, the by0, and the cz0 are all constants. Because a is part of our vector, x0 was part of the point. Those are two numbers, multiply them together, you get a number. So the tail end here, those last three are numbers. What we do is we define these three numbers to be equal to d. And notice the negative signs, this is important. Minus, minus, minus. Negative ax0 minus by0 minus cz0 is defined to be d. And if we let that be d, then we get the linear equation. It's the ax plus the by plus the cz plus all this junk, which is just a number. We call it d. Equals 0 is the linear equation of a plane. All right, let's move through this. Find the equation of the plane through 3 points. All right, who's going to be the one who tells me what I need? What do I need? I need a point and a normal. Okay? For a line, we needed r0, the vector r0, and we needed v, the direction vector. For the equation of a plane, I need a point on the plane, and I need a normal vector to the plane. So the point should be pretty easy, right? Should I have 3 to choose from? So I'm going to just pick 1, 2, 14. What about a normal vector? So you got to go back to that picture. We have 3 points, right? The cross product of the vector between two of, yeah, so we have to kind of do a little work here. We're going to have to pick a point. We're going to have to go from here to here. We're going to, I don't know, I'm just going to call that, I don't want to call it n. I'm going to call it u1. And then I'm going to create another vector over here, u2. And then when I cross the two together, that'll give me a vector that's coming out of the plane. You don't need to draw this, but let's just imagine that there's, you know, a plane that those 3 points go through. Terrible, but that's what it is, okay? So my normal vector comes out of this, should come out like this, should be perpendicular to the plane. That's my normal vector. So what's u1? Yeah, we have to maybe do some labeling here, huh? Do y'all want to call this point over here the 1, 2, 14? Maybe call the one up here -2, -5, -1. Do y'all see that there's like multiple ways to do this? Like you could pick different points and different vectors. We should all come up with the same equation though. Or a scalar multiple of the equation. So those are my 3 points, right? What's u1 then? If I define my points that way, what's u1? -3, -7, -15, and then what's u2? Did I get that right? Okay. And then 11, -5, -13. And now my normal vector is U1 cross U2. Good, I'm here in calculators. And now I need to cross those two. Now, I had a couple students ask me about some other ways of doing cross product by hand. There are so many ways. I said the calculator, you know. The thing is, some of the problems that you do by hand, even though it's cool, the numbers, if they're too big, it can still be a pain. So, you know, this is where I'd expect you to break your calculator out and do this. Who has still not figured out how to do cross product on their calculator? Do you have one? Okay. You need to make sure you can do that, okay? Can I? It depends on your calculator, so it's kind of hard for me to I'd be happy to show you maybe at the end. What kind do you have? 84 also? Yeah, you probably have to write a program for it. Who came by my office and wrote a program? Okay, how hard was that? It's really easy. I mean, seriously, it's really, really easy. Once you do it, it's actually even better than the built-in one because it'll give you the cross product and the magnitude of the cross product. So, take about 5-10 minutes. Okay, 16, negative 204. Who made this problem? Okay, 92. All right. Is that what? That's negative 16, negative 204, 92. Positive 16. I'm curious. Are those all divisible? They're all divisible by 2, aren't they? Can I go more than 2? 4? Can I go more than 4? No? Yeah, so all I'm saying is that's a normal vector, right? But remember, the normal vector came out of the plane, didn't it? Like this? And wouldn't any scalar multiple of that still come out of the plane? So I'm free to use that as my n if I want, but I can also scale it if I don't want my numbers to be as big. It's up to me. I'm going to scale it just because I don't want that to be so big. So I'm going to scale n, divide everything by 4. So 1/4 of n is my new n, is 4, negative 51, 23. You don't have to do that step. This is going to be equal to, and I'm going to change colors here. This is my new n, okay? My new n, new and improved n. Still a normal vector, still points perpendicular out of the plane, but it is a little bit shorter than the one we had before. All right, so what's the equation? What's the equation of a plane? Oh, I really didn't want to do that. This program I'm having a little trouble with. I'm supposed to be able to hit backspace right now, and it's supposed to all come back, and it doesn't, and so I just lost that. Oh well, too late. That's the one little snag I've found in this program. All right, so what's the equation? The equation is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equals 0, right? That's the equation of a plane? I know A, B, and C, don't I? What are they? What's A, B, C? Yeah, it's the A, the B, the C. So the numbers in front, A, B, and C, are the direction of the normal. So I have 4 x minus, now what's x naught? Yeah, that's, remember when we picked a point earlier? It was x naught, y naught, z naught. So it's 4 minus 1, or 4 times x minus 1, then minus 51, parentheses y, minus 2, plus 23, z, minus 14, equals 0. Now let's distribute everything through. 4x minus 4 minus 51y plus 102 plus 23z minus 233. Is it 320? Yeah, that sounds about right. 322 equals 0. And then I have 4x minus 51y plus 23z. Now put these numbers together. The negative 4, the 102, and negative 322. What do you get there? 420? No, it's negative there. Yeah. 224? Negative 224? Negative 271? Negative 224, okay. Equals 0. All right. That's it right there. Now, we need to identify that. Remember I said in the formula that when you do this multiplication through, you're going to have a bunch of numbers, and that we say that those numbers are equal to D. Remember that? But it's actually a little tricky on the sign here. Ooh. So everything that comes together here, right here, this right here, is D. Okay, that's D. When you take that to the other side of the equation, it's negative D on the other side. So if I asked you right now, if I wrote that equation down right there, and I asked you what's D, what would you tell me? Negative 224. But if I do what we would naturally want to do here, and take that constant to the other side, if I just started the problem like this and said, hey everyone, what's D? You would have to say negative 224. You'd have to understand that what's on that side is negative D. So if the constant's on the right side, that's negative D. If you move it to the left, that's D. What is, when you have the equation of a plane, okay, it's written like this, what's kind of staring at you, just looking at you? What is given to you when you write the equation of a plane out? What's just staring right at you? What's there? Do you see it? Maybe it's not staring hard enough. What are those three numbers? That's your normal vector. Okay? That is something extremely important about planes. When you write the equation of a plane out in the form ax plus by plus ax plus by plus cz equals, take the d to the other side, equals negative d, the a, the b, and the c are your normal vector. Always. And that's going to be very useful to us. So we're done. That's the equation. Yes, your D will change depending on, your plane's point. Yes. Y'all hanging in there? All right, let's look at some graphs here. Angles between two planes. Now, we've already talked about angles between lines, right? You have two vectors out there, angles between those lines. But what about two planes sitting out in space? If you want to know the angle between two planes, all you have to do is look at their normal vectors. Because if I have a plane sitting out there in space, its normal vector is 90 degrees different than the plane's direction, isn't it? Right? It's 90 degrees off, orthogonal. And then if I had some other plane sitting here, its direction, the normal is 90 off of that. So if all I do is look at the normal of this one and the normal of this one, the angle between those two normals should be equivalent to the angle between the two planes because they both differ by 90. And this little visual just kind of tries to help you see that. Here are two planes. Let me see if I can really try and point out. Do y'all see where they intersect there? Kind of like at this little cross here, like that. We have an angle in here, don't we? God dang it. I turned to look at y'all and I let it go. Okay, there's my little angle in there. Now I'm going to show you the normals popping out of those. The angle between those are the normals just sitting on the plane. What I'm going to do is actually move the normals. See, those are just kind of sitting there. If I move them to where they intersect each other, the two planes, if I move the two normals, slide them over, then if we turn it sideways again, and let me take the original normals off, then there we go. I think that'll do it. Then we have the angle here should be the same as the angle here. Y'all agree? That's what we have. So anytime you want to know the angle between two planes, all you need to do is find the angle between their normals. If you do that, you're in business. Next one. Two planes are parallel if and only if their normals are scalar multiples. Does that make sense? I mean, we've already talked about parallel planes would look like that, right? And if we look at their normals should point in the same direction. They don't have to be the same direction, they have to be scalar multiples. Remember, vectors can be pointing in the opposite directions and be parallel still, right? So they just have to be scalar multiples. Hopefully you can convince yourself by looking at those two, those are pointed in the same direction. Okay, next. Two planes are perpendicular or orthogonal if and only if what then? Their normals are orthogonal. Dot product is 0. So these are all just results. Find the angle between these planes. All right. On P1, which stands for plane 1, it has a normal vector, doesn't it? And P2 has its own normal vector, which I'll call N2. What is N1? 1, 1, 1. Where is that coming from? 1, 1, 1. Coefficients of x, y, z. What's the normal vector for plane 2? 2, negative 4, 7, right? What's the angle between them? How do you find the angle? Oh, remember this? Angle equals cosine inverse u dot v, which here will be n1 dot n2 over magnitude n1, magnitude n2. Compute. I won't do it. But I mean, that's how the problem's done. That's pretty straightforward, right? I mean, pick off the normal vectors, compute the angle. The angle between any two vectors can be found using that equation. Yes. In this case, the vectors we want happen to be the normals of two planes. And I proceed. All right. The line of intersection of two planes. Hey, isn't this part of your take-home? Doesn't it talk about line of intersection of two planes? Something like that? The mini test doesn't have that? Let me, can I see it real quick? Is it, who has it? Find, this is number 6 on your mini test. Find the vector equation of the line. Hey, we're talking about that today. Passing through the center of the sphere, blah, 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 and the point of intersection of the line with the plane. Okay, never mind. It's the intersection of two planes. This one, test problem is talking about the intersection of a line and a plane. Didn't we do a line in the plane a little while ago? We asked where a line hits the YZ. Huh. Okay. I'm just saying, I mean, we did, right? Something like that? All right. All right, so how do you find, oh no, this isn't a question. It's saying, what is the line of intersection of two planes? So if we have two planes and they do hit each other, they intersect at a line, don't they? That blue line is being highlighted here. Man, for some reason, it's when I look up there, it just spatially doesn't work for me. Okay, hopefully y'all see that. We're looking straight on to the intersection there, and now I pivoted the front end down. Do y'all see that? Okay, two planes hit the blue line. Question is, how do we find the equation of that line? The vector equation of that line. It's a line, right? What do we need to find the vector equation of any line? A point and a direction, right? A point and direction. Now watch the way we're going to get this. This freaking gives me goosebumps. Okay, look at this. First of all, look at the normals of the planes, okay? Those are the normals of the planes. There they are, just sitting out there in space. Do you agree that the green one looks perpendicular to its plane? Do you agree that the orange one looks perpendicular to its plane? But those are just normal vectors. They're just sitting out there floating around, right? The normal vector can be anywhere on the plane, right? Can move it around. So what I'm going to do is conveniently slide them onto the plane, onto the blue line. Just move them down. I'm not going to change their direction, just slide them. And when I slide them to the blue, now they're both there. Do y'all agree I didn't cheat? The orange is still pointed in the same direction as the orange, and the green is still green? We're okay? Now I'm going to take the other ones out of there so that they don't confuse us. So now we've got two normals. Tell me how I can find the direction of that blue line, the direction. Cross those two vectors. Because when you cross those two, where's it got to come out? Right there. See it? And it is on the blue. So therefore, we have a direction of the blue line. What else do you need? A point. Can you find a point of intersection of two planes? Well, we'll see. We're about to do one, I'm saying. We'll see that way, all right? That's pretty cool, right? I mean, you have two planes. You want to find the direction of the line of intersection. You cross the normals, and you got your direction. I don't know about you, but how many of you, like that visual kind of helped you see it? I mean, like, can you see it off that visual? I just don't understand how you learn this without the visual. I mean, I could tell you the direction of the line of intersection is the cross product of the normal vectors. But that, to me, doesn't make a whole lot of sense. It's just like, okay, that's what I'll do then. You know, it doesn't really, the visual part of this is a little bit easier, I think, to understand. Hopefully it is for you. That's why I do this. Okay, here we go. Find the vector equation of the line that of intersection of these two planes. Vector equation of the line of intersection of these two planes. So moving quickly, what is the, what do we need for our, what is the problem asking for here? Vector equation of a line? So I need to find some R of t. And we know for R of t, we're going to need R naught plus V t, or TV. I did it TV, didn't I? Yeah, it doesn't matter. But I'll stick with what I've been doing. TV. So I need a point and I need a direction. Well, what do you want to start with? Point or direction? You want to do direction? Because we just talked about the cross of the normals, right? So if I can grab the normals off these, cross them real quick, that'll give me my V, won't it? So I'm going to put this normal is 1, 1, 1. This normal is 2, negative 4, 7. Someone's using the program they just wrote to, or just using their built-in or whatever, to cross these for me. And that will be V, won't it? Or a scalar multiple, yeah. Anyone have it? Negative 5, oh, 11, negative 5, negative 6. 11, negative 5, negative 6. And then, what do we do now? Find a point. Now, just any point. It's got to satisfy, it's got to live on both planes, right? So I need to find basically an x naught, y naught, z naught on P1 and P2. Well, this is actually a lot easier than it may sound, because you can try some things for x and y and z and see if they work. Like, how about just for the hell of it, let's let z be 0. Okay, let's just try it. What would happen if z is 0? Wouldn't we get the two equations? The two planes would turn into what? X plus y equals 5, and the other one would turn into 2x minus 4y equals 10. What I'm saying is that by letting z be 0, those two plane equations turn into those two equations, and that's a system of two equations and two unknowns. So you can solve that for x and y. And we should be able to get a solution for that, unless they're the same line. No, they're not. There's a negative between there. Right? There's a negative right in there. That saved me. If they were the same line, they're infinite solutions. So, yeah, we can do several things here, or substitution. At this point, I would expect everyone in this class to be able to solve a system like a little linear system like that. But we have to do it, unfortunately. I'm going to subtract that row from that one. So it's going to become x, subtract negative 5y equals 5. I believe I get y is negative 1. If y is negative 1, then x is 6. Let me just try it. 6, negative 1, 0. Does that work? Try it in the first equation up here in P1. 6, negative 1, 0 work? Give you a true statement? 6, I'm trying 6 for x, y for negative 1 for y, and 0 for z. Looks good on the first equation. How about second equation? 12, take away 4. Or sorry, yeah, adds negative 12 plus 4, and then minus 10. Does that work? Oh, wait, I forgot. Do y'all see what I did? Right here. Do y'all see what I did there? Oh, that's okay. All right, I'm sitting here. I sound like an ass. I'm sitting here like everyone should be able to do this. I was trying to do it too quickly. Let me just take my time through this. Maybe, I don't know. I'm trying to get through enough of this material, but I'll slow down. I want to do it right. So I'm trying to solve this system. Again, you have different options here. I do x. I'm going to solve the first one for x. I'm doing substitution. Replace that into the second equation. Yeah, I did. Yeah. Oh, do I have those backwards? All right. I'm not becoming that old professor who doesn't know what the hell he's doing up there, okay? It's just tangent. Not yet. Yeah, that can be. All right, 10. What do we get here? 10 minus 6y equals 10. Y equals 0. That's not working. It works. Who solved it? Who has it? Does anyone have it? What do you have? 6 what? 500. Okay, let's just go with that. I'm not gonna. I believe it works. this should have worked. I don't know where I went wrong here. Z is 0. Z is 0 makes the first equation this one. Z is 0 here makes the second one 2x minus 4y. Move the 10 over is this. Subtract, you get x. Subtract, you get negative 5y. Subtract is 5. Somewhere in there. I subtracted the rows. But in any event, we should be able to do that. I really don't want to put more time into this than we have to. We have a solution, right? You could find it would have worked with Z0. It would work. You get 500 is a solution. Y'all agree? That's all we needed was a point. We got one. So now let's come up with the equation of the vector equation of the line. So I'm back up top here. Back up to that top right corner. It's R of t equals, what's R naught for us? 500. And what is the t, and then v is 11, negative 5, negative 6. And then you could put them together and you would have your vector equation. You need to put them together, but I'm going to move on. Whoa. Yeah, I think it did, but I'm going to do it again just in case. All right. I know we're running really low on time here. What's next? Distances. Your your mini exam has distances on it, doesn't it? No? Okay. Then that should be enough. Let me see that one more time. Let's talk. Does everyone have their mini tests with them or not? Yeah, you should be able to do 6 now. We're going to have to wait on distances. I don't want to try and force distances in the last 10 minutes. You have a mini exam due, but you also have some homework I'd like you to do. Oh, and that handout. And the sign-in sheet. Sign-in sheet's coming around. Here you go.
I literally had no idea what was going on.
Here you go. You know what? Two more back there. Did everyone get one over here? Yes? Okay, look, for homework, what I'd like for you to do is this handout that I just gave you. I'm also going to give you some homework out of the book at some point, not tonight, okay? I want you to look at this for Wednesday. These are the things I think in this section, 10.5, these are the skills you should be able to come out of this with. So, you know, part A here, everyone needs to be able to find the vector equation of a line given 2 points. The next one, find the vector equation of a line through a given point and parallel to some other line. And then I keep on going through all these different scenarios. And then I give you an example of each one. So I'd like to see if you can work through these. I think if you can work through all these, you've got a pretty good idea of the relationship between lines and planes. What you won't be able to do is any distances, but I do not believe I ask you any distances in this homework set, so you'll be perfectly fine. What else? Sign-in sheets going around? What is what leading up to? Well, part of the planes idea is from, you know, remember back in Cal 1 we did like tangent lines? Well, in Cal 3, we're going to be looking at a surface, something like this. You know, that's not a good, but imagine a three-dimensional surface. And imagine taking, more like a hilltop in this surface, and we don't have tangent lines. Instead, we have tangent planes, right? You don't have, since it's three-dimensional, imagine pivoting. If you have a basketball, there's a plane that sits on the top, where you can pivot that around. So we have to have a good idea of what planes, how to work with planes before we can start making them our tangent lines. That's just one. That's one. Oh yeah. Don't worry. Don't worry. It's just now starting to get a little interesting in here. As soon as we finish this up, we're going to spend some time in 10.6 and 7 doing vector equations, these weird like space trajectories and stuff. All of it's going to be somehow used in calculus that we're going to do later on. Yeah. You just have to hang tight. It's all coming. We're early. The homework is the handout, and the thing, of course, the mini exam is due. And you can do that problem. Oh, I was going to talk that last problem. If you have any questions on that last problem, you just let me know. Come talk to me. You should be able to do it now. I think I'm done, yeah. Good luck, everyone. See you on Wednesday.
You happen to have a chance where I can check with them on that problem?
Yeah, let me turn this off and see if it's gonna